In this unit, we're taking a look at trigonometry, and we're going to start with similar triangles. So a couple definitions. First off, congruent figures. We're focused on triangles, but congruency can work with any figure. Congruent figures have the exact same size and shape. They are identical. Similar figures have the same shape, but they're different sizes. One is a scaled up version of the other. So if we take a look at our triangles here, we have this 3, 4, 5 right angle triangle, and we have a 3, 4, 5 right angle triangle. They are exact copies of each other. If I was to cut this out and put it on top of here, it would overlap perfectly. Now in the case over here, we have the same proportions. So 3 by 3 and root 9 would be the hypotenuse. Well, if we double 3, we get 6. If we double 3, we get 6. And if we double root 9, we get 2 root 9. That there is the same shape, but it's a different size. So that's a similar set of triangles. They have the same shape, but different sizes. It's important to note that similar shapes have all sides corresponding. So all the sides have a corresponding side that is scaled up. So the root 9 matches with the 2, the root 3 matches with the 6, or sorry, just the 3 matches with the 6, and this 3 matches with the 6. They have a matching side. The sides differ by a common multiple. In the case above, the common multiple was 2. Similar shapes have all angles corresponding, so they have all the angles match up as well. So all the angles in these shapes match up. The right angle is found in between the 6s. The right angle is found in between the 3s. Those angles would match up. The hypotenuse is here, and these respective angles would be exactly the same. These are isosceles triangles in this case, so these both would be 45 degrees, and they all match up. And so all the angles and sides all match up in these triangles when they are similar. So that helps us identify similar triangles if they have some of these cases. If they have all 3 sides the same, or they have all 3 angles the same, they're going to have some sort of similarity. So identifying some similar triangles, how are they similar? We have a pair of triangles here, and you can see there is a larger triangle, ABC, okay, this big triangle, and then there's a smaller triangle inside. And they're similar triangles. How do we know that? Well, triangle ABC, and the notation you'll often see for similar in math is a little squiggly line like that. Is similar to, and now we got to label this right. We can't just say DEC or CDE. CDE would make sense because it's alphabetical order, but angle A and angle D, those are in the same spots. These would be parallel lines, and this would be that F pattern of the parallel line theorems. So this here, A and D are in the same spot. B and E are both at that right angle. So B matches up with E, and then angle C is angle C in both cases. So we have these two triangles. ABC is similar to DEC, and it's in that order that we list them. So every angle that matches with its corresponding angle, and then we'd have side AB matching with side DE, side BC matching with side EC, sorry, and then side AC matching with side DC. So we have these matching triangles. How do we know they're similar? Again, we mentioned some of that already. Angle A and angle D are going to be the same because of the parallel line theorem. Without that, though, we don't even need to use any crazy theorems like that. We could just say that, well, angle C equals angle C because they're the same. So angle C and angle C are it's just angle C. I mean, this one angle. B and E. So angle B and angle E are the same because they both equal 90 degrees, as noted. And then because we have 180 degrees in a triangle, angle A equals angle D because 180 degrees is the sum of the angles in a triangle. So something like that could give us our statement to show that this is similar. That would be angle, angle, angle is the methodology. Here's another example. We have a pair of triangles here on the diagonal. And again, we have a nice little setup here. We could check angles and we can check sides in this one very easily. So the sides are listed. So if we look here, if we were to take this big triangle and pivot it at this point, we'd flip it around and then you'd see that it would line up similar to the last one. So the 4 and the 2 match, the 6 and the 3 match, and then 2 roots 13 and root 13 match. So the sides of the small triangle are 1/2 the large triangle. Also, we have that right angle that matches. This here is the opposite angles. Opposite angles are going to be the same, and that would then result in these two angles being the same. In a triangle, once you have two angles the same, the third angle automatically has to be the same. So something like the sides of the small triangle are 1/2 the size of the large triangle, or vice versa, saying that the large triangle is double the small triangle would perfectly work. When we're given similar triangles, so here we're being told that triangle ABC and XYZ are similar. Anytime we have those similar triangles, we will have the fact that side AB is divided by side XY. So these sides here, these matching corresponding sides, will be in the same ratio as, BC divided by YZ. Will be the same ratio as CA divided by ZX. So the pairs of sides, each corresponding pair will be in the same ratio as the other ones. And we see that here. We have 6 divided by 3 is 2, 4 divided by 2 is 2, 2 root 13 divided by root 13 is 2. So this here is double that, and so we have that multiple. Here it's the same idea, and we can be multiplying by a fraction, or if we did this the other way and said root 13 divided by 2 root 13, and so on. So we can use this information and knowledge to solve similar triangle problems. So one of the common use and easy to understand use is determining the height of a tree. So oftentimes it's difficult to climb up a tree and get to the top and measure all the way down accurately, even if you have a nice robust tree that you could for some reason climb to the top of without tipping anything and bending anything. You're going to have trouble getting a good tape measure all the way straight up and accurately measuring that. So instead, what we can do is use similar triangles to measure the height of a tree. And it makes it a lot easier than trying to climb up a tree. So in this case here, we got Lois is measuring the height of a tree by measuring the length of the tree's shadow, which is 15 meters. She then puts a meter stick at the ground on the ground vertically and measures its shadow at 1.5 meters. And how tall will she find the tree to be? Well, what's happening here is we got this tree. So we got some tree here. I'm going to make it a little bit longer so that it touches on a line. There we go. So I got this tree here, and then I have, and it's casting a 15-meter shadow. Now, our triangle comes in because that shadow is being made by the sun shining its rays down, and one of those is catching the top of the tree, and then the shadow is coming down like this. So essentially what we have here is ourselves a right triangle with the ground, the tree, and the shadow. In the case of the meter stick, it's being hit by the same rays of the sun, so as long as it's not too far away, we're going to have this meter stick sticking out of the ground. It's going to get hit by the sun and cast a shadow. And this sun's angle is going to be the same as on the tree, so we're going to have a similar angle on this triangle here as well. And thus we have similar triangles because we'll have the right angle and the angle that the sun makes matching. So now we can use these similar triangles, that's 1 meter, 1.5 meters, to solve this using one of these proportions. So if we just take the proportion of one side over the other equals one side of the other, as long as we use the matching triangles. So we are looking for this here, the height of the tree. So the height of the tree divided by the height of the meter stick, 1, equals the tree shadow. I started with a tree on top because I was looking for the tree, so I keep the tree on top here, divided by the meter stick shadow. So tree over tree, shadow over shadow, and I'm doing them again in the order, keeping the same order. So the tree setup is on top over the meter stick setup. So here is where you would do your cross multiplying. It's not when there's a multiplication sign, but we multiply across the equal sign. Essentially, we're just doing this cross. We don't have to do it here because it's a 1, but we'll do it just to show. So this is 15 times 1 divided by 1.5. And so we do all that. 15 times 1 is 15. 15 divided by 1.5 is 10. And we get the height of our tree as 10 meters. So whenever you have a situation where you can set up two similar triangles, you can find the matching sides and set them one over the other, as long as the same shape is on top and then the same shape's on the bottom. And you can then do your cross multiplying and solve. And it'll always, if you set up your missing value on top all the time, then it'll always just be cross multiply this number with the top and then divide by the bottom, and you'll get your result.